Our project is motivated by three simple facts. One, climate change is kind of a big, scary thing. It's going to affect what and how we do business. Two, there's a lot of big, sexy fish that we care about within this part of the world. Trout and salmon in particular support important recreational and commercial fisheries. And three, we don't have good stream and river temperature climate scenarios really to facilitate any sort of strategic planning across the basin, despite the fact that we're spending hundreds of millions of dollars of taxpayer dollars every year to try to conserve and hang on to some of these critters. So we're basically trying to fill that void and develop some regional stream temperature scenarios that can facilitate that planning. So this is our stream temperature team. So there's about 14 people on this team, 5 different agencies represented, and we're funded by primarily the Great Northern Landscape Conservation Cooperative, and then also the North Pacific Landscape Conservation Cooperative as we begin moving into this part of the world. And so this is basically the issue we're trying to address. How do we translate this big global phenomenon down to a more local scale so that we've got good enough local information to empower local decision making? And this is kind of where, I work for the Forest Service, so we've got a lot of people on the ground on forests, and they haven't had good enough information really to understand this yet. And so we're just basically adding a few links in the chain by working through regional climate models and then developing river network thermal models that are linked together so that they hopefully will have that level of resolution that they need to facilitate local project scale implementation. And we're going to be forced to make decisions. We want to try to give people good enough information that they can make decisions about where they're going to allocate the resources that they have in terms of trying to do stream rehabilitation projects or other things. And as I mentioned before, there's a lot on the line in this part of the world. Certainly there are a lot of important recreational fisheries, commercial fisheries for salmon and trout species. We've also got a lot of ESA listed species, and those critters occur in rivers and streams across hundreds of millions of acres in the Northwest, and it affects land use management and planning decisions on those acres. And so we're spending a lot of money within the basin to try to hang on and conserve these species. This estimate's getting to be a little bit dated now, but ISAB and ISRP estimated as of 5 or 6 years ago that we'd spent $4 billion trying to recover some of these species. So it's not a trivial issue in terms of trying to better understand how climate might affect aquatic critters across the region. And so one of the caveats on doing that for streams and rivers is that we don't have climate models that are specific to aquatic ecosystems. So, and that's very much in contrast to the average. When you go to climate meetings, they've got dozens of models. I don't know how they keep them all straight, and I think that's probably why they invented, the ensemble averaging, is so we can kind of use everybody's model and no one's model gets left out. But we don't have even one realization yet of this for streams and rivers in the Northwest, and so we're trying to build our first one. And we need to do that because air temperature, the spatial patterns in air temperature do not equal stream temperature. In complex topographies like the mountainous and desert regions of the Northwest, there's a lot of things that affect stream heat budgets on a local scale, and so that makes them deviate from what local air temperature patterns are a lot of times. And right now, when we do sort of regional broad-scale climate vulnerability assessments for some of the fish species, we're forced to incorporate all of this imprecision into those models because we don't have good enough local information. So one of the nice things about the Pacific Northwest, though, is that the regional regulatory and management communities have been collecting a ton of stream temperature data over the last 20 or so years. So I like to refer to this as our stealth sensor network because we've literally got an army of people that have been running around the woods now, largely in uncoordinated fashion. The right hand doesn't know what the left hand is doing, and this is a massive thing that's out there, and we didn't even realize that we had it until we started pulling this database together. And so this is what we call Norwest. It's probably the world's largest stream temperature database. There are more than 45 million hourly records within this database, 15,000 unique stream sites represented, and we've had data contributed to this project then from 60 different state, federal, and tribal agencies. And this map then is a little bit outdated. It's over a year old. There are actually more dots on the map than what I'm currently showing. And we're using that information then with a type of new statistical model that's built specifically for stream networks that some of our project collaborators have been developing. I won't go into more details there, but they work really, really well with these sorts of big found databases that are aggregated from multiple sources. And the basic idea then is to use the data in Norwest with these stream temperature network models to downscale climate effects and create cross-jurisdictional maps of climate scenarios on stream networks so that we've got a consistent datum then to use for strategic assessments across all of the 400,000 or so stream kilometers in the Northwest. And so just as an example then of kind of the process that we go through within an individual river basin, there's too much data out there to be able to fit it all in one model, so we're kind of chunking it up as we work through our region. But this is basically the set of steps that we go through, and here we're looking at the Clearwater River Basin in North Idaho. In that particular landscape then, there are more than 5,000 summers of monitoring effort at 1,000 stream sites over this 19-year period. Not all of these points have been obviously monitored each of those 19 summers, but you know, there could be 1 year, there could be 10 years of data at those. There's a tremendous amount of data that we're extracting information from. And two, then there's also a lot of climatic variability embedded in these temperature data sets. So if you just go back in time, looking at the range of, or the difference in average summer air temperatures over this period of time, they span a 4 degrees Celsius range, spans about a 3-fold range in summer discharge. And so this is nice because when we then use the model to make future scenarios and predictions, a lot of times we're not actually extrapolating beyond the range of what we've already observed, at least until we get out into the latter half of this century. So that gives us more confidence that our future projections potentially are going to be accurate, as long as the climate projections that the climate modelers give us are also accurate, because that's ultimately what drives our model. And so in terms of fitting the model, then this is pretty par for the course in terms of what we're seeing over and over again with these found databases and using it with these spatial statistical models. We can typically explain 90% or so of the variation in these databases and do so with less than an average degree prediction error. And we're predicting stream temperatures in from a suite of spatial covariates that all come off of previously published nationally available geospatial layers, and then also linking the interannual changes in stream temperatures to discharge, which is measured at the USGS gauges within that landscape, and air temperatures as represented from Steve Hostetler's Reg CM3 and CEPRI analysis. So we've got good representations and of how things vary through time on that particular landscape from these climate driving variables. And so once we've built the model, then we've got a tool that we can use to represent different scenarios. We basically just have to adjust air temperature and discharge values to recreate or make predictions about what we think the future could look like. We could also adjust the canopy variables if we wanted to play some vegetation scenarios. We haven't done that at this point. We're building a bunch of climate scenarios then where we're actually doing a bunch of historical scenarios as well. So if people want to hindcast and kind of link some of their biological data sets to what the thermal patterns were within a particular year, they can do that. And then we're creating the standard set of IPCC scenarios for the A1B warming scenario at this point for the 2040s and 2080s. And so we're in the process now of linking our models to some of the SIG scenarios using the A1B ensemble averages that SIG has put out in the Delta hybrid method. And these predictions then are just using our model to translate the SIG projections for future change in air temperature and runoff to stream temperature change across the river basin. There's 5 river basins we've completed so far. And for the 2040s, those are the lighter bars. We're seeing a range of future changes from the upper Snake River and Bear River of about 0.7 degrees Celsius by mid-century to the Clearwater, which potentially is going to warm up at twice that rate. And then the darker red bars are the predictions for the 2080s. One thing to keep in mind when you think about climate change in streams is that streams warm more slowly than air temperatures do. And so kind of a rule of thumb to go by is that streams warm up about half as fast as air temperatures change. And so here we're using the model then on that same Clearwater landscape, but now we're just using it to create or map out a series of predictions representing, in this case, a historic scenario across this river basin. And these orange tendrils those are the main stem rivers in this system. Those are always the lowest elevation parts of that network, and so they're also going to be the warmest. And I'll just flip through what the future scenarios would look like then, and you can get a sense of how that thermalscape may change. We're making these predictions at a 1 kilometer resolution. I'm a fish biologist by trade, and so everything I've just talked about is actually kind of boring to me. It's just physics. It's not, doesn't get to be interesting until you actually pass that information through a fish and you start to translate it into habitat. And so that's another big part of this project then, is to basically use these standardized temperature maps, combine those with big regional fish surveys, and if we thought there was a lot of stream temperature data out there, boy, there's even more fish survey data. Right now, Seth Wenger is leading this particular part of the effort, and he's got more than 30,000 different sites on streams across Idaho, Montana, and Wyoming where they've done fish surveys. Basically, we're going to plop those down on these temperature maps and derive good defensible estimates of what's too warm, what's too cold, and what's optimal for some of these species. And when you do that, then you can take those thermal maps that we just looked at for the Clearwater and translate those to effects on species X, Y, or Z. Here we're just looking at what the Clearwater would look like through the eyes of a cutthroat trout. For the historic period, the black areas are thermally suitable, blue areas are too cold, and the red areas then are too warm. If you flip forward, we do see some loss of areas on the warm side of the spectrum at the downstream part of the system, but at the same time, they've got an elevational refuge that they can move up into, and so climate change for this particular critter in this particular landscape isn't necessarily going to be a bad thing. Contrast that then to what we might see for bull trout. This critter has a much more restricted thermal niche in terms of needing cold water, and so they're already a lot of times backed up into these systems as far as they can be, and so if we flip through that same sequence there, we can see that indeed they are going to lose a lot of habitat, and so hopefully we can start to provide good enough information on where that habitat is going to persist that people can start to use it in their conservation planning. I'll probably just skip through this, but the model does recreate and capture the fact that there is a lot of spatial variability, even at a local scale, in terms of how fast habitat's going to go away, and that's due to a concept called climate velocity. A temperature isotherm just moves a lot faster through a flat space than it does through a steep place, and the model faithfully recreates that. And so if you take a difference map and look at a future scenario from a good representation of the historic scenario, you can start to highlight places that are kind of on the edge for a particular species. That's the blue reaches in this particular graphic. Those are going to be the first places that are going to go away for bull trout in this particular landscape. And so we can start to reduce that overall network and look at it a little more from a tactical standpoint in terms of where we're going to get the biggest bang for our buck in terms of investing to try to keep it around. And so there's a lot of things that we can be doing in terms of trying to combat the effects of climate change in these systems, but we're going to need to make choices about where we do those things. And so, this approach to doing and building this model is kind of a crowdsourcing approach to science. So the hope is, too, that as we go along and we use and pull together these databases, we're actually building a community of users that are engaged in this process. We've literally gotten and are using data from hundreds of biologists and hydrologists across the region. And so hopefully everyone kind of feels like they have some skin in the game. And these are the people that are on the front lines that are going to have to make decisions a lot of times about what they do from a practical standpoint in terms of dealing with climate change. If you want to access some of this data, we've got a website up. Just Google search us on the word Norwest, and you can find us. We've got raw temperature data summaries there if you're interested in doing research, or GIS summaries of the climate scenarios. A lot of different projects that this is already starting to synergize with. I won't go into details there, but all this stuff is basically modular, so it starts to snap together, and hopefully the overall whole sums to something that's much greater than the parts. In terms of the schedule, the green places are the places that we've so far completed, so most of Idaho and western Montana. We're just now rotating into southeast Oregon, and we're going to work our way across the state over the next 6 to 8 months. And a special thanks then to these 60 different partner agencies. A lot of different groups have contributed data to this effort. And at present, this is where we are in terms of developing that stream thermalscape, or as we like to call it, the blob map. Tremendous amount of thermal diversity out there, so there's probably going to be room for some of these species in different places if we kind of know where to help them along. Thank you.